Okay, at the end of this part related to the electronic material, let me restart now from the introduction related to the discrete systems, and in particular continuous discrete systems. In order to introduce, I think at the end of today or probably next week, the model predictive control, linear model predictive control, about which is discrete, or at least what I will consider in this course a discrete method. Of course, we can do everything also in nonlinear, and this is based on Lyapunov. I will flesh out a little bit what eventually we can do, but I don't have time to tell you about these methods. But in any case, if you consider Lyapunov, which you know in continuous, and then considering this concept on discretization, of course I cannot pretend in a question or in a problem in the exam. Uh, I will not propose any questions about discrete model predictive control, yes, but in continuous. Excuse me, in linear systems, in linear form. I don't pretend anything about nonlinear, but in the near future, you can consider again to mix a little bit this Lyapunov aspect. I will tell you a little bit in discrete and what we learn in general until now, and you can guess, of course, in your university, I know that there are many experts in discrete nonlinear control. This means you will have the possibility to go in depth. I would like to say also based on this knowledge, on this selection of topics. Again, today we will go ahead with this basic knowledge. I will conclude this basic knowledge using showing you, I think, just one controller, the most important, probably the most complete, which we consider an integral action, which is present in the application, robotic application, automation, almost always, not always, but almost always. Therefore, I will consider also today this variation, and together with the state space part of the controller, which is also, for the reason which I already clarified in continuous, very often used. Next week, model predictive control. It could be that I will be able to introduce today, but I'm not sure. Okay, let me switch in the lateral camera. Let me really sum up really quickly what we did last time, and then we will start slowly from the point where we left. This material is not in the WeCamp, at least not yet, but I will generate in a folder with the title discrete control, something like that. No? Did you see that I organized a bit, let me say, per topics? Continuous, linear continuous. I don't remember what I wrote anyway, but it's in accordance with the course you are able to orient. Slide remote control, everything continuous. Then we will switch, let me say, into discrete methods or discrete system in accordance with the time which I have. I have to select, therefore the title, what I think is important to know in this preliminary course. Next week, we have here at my university a guest from your university, probably you know, Pavel, which is who is working with Professor Andrzej Bastoczewski. Let me see if I am able to tell you the family name, Latosinski. I don't know if I pronounce it correctly. Is a friend of mine. I probably you know him from some lecture or some exercises as a collaborator, and a scientist, very good scientist, who is working with Professor Andrzej Bastoczewski. 1 second, I connect with the lateral camera. This is already something which challenged me, but I think that I was able to do. Now, let me switch on the lateral camera. In any case, let me... Oh, why it doesn't work? Oh, here. Quickly to recap, because always at the end of the lecture, at each lecture at the end, I always more confused than at the beginning. Why it doesn't work? Okay, now probably the system needs time to recognize the connections and so on. Yeah. You remember I tried to introduce a little bit a method together with the concept of a discrete system. Very quickly. What is the meaning of emulation methods? We can consider two possible methods. One is the evolution method, and the other one is direct method. Let me show this one, which nevertheless is extremely useful, because the concept of the emulation method means, or is based, or the words emulation method or the methods is based on the continuous design, exactly as we did until now, the continuous of the controller, of course. The system basically, or at least we assume that we are working with continuous systems, physically, technologically, very often, not always. Very often we have to do with the continuous system. This means the states change continuously over time. We don't have a system which has state which change, let me say, the discrete changes, the discrete states. This is a concept a little bit difficult, but if you think about physical system, the velocity, positions, in accordance to what we observe in the context of possible phenomenologies, we observe that the states change over time continuously, or at least it seems to be something like that. We know that the quantity mechanics say this is not exactly so, but in a microscope, in the macroscopic, let me say, in the macroscopic representation of the system, of the physical system, we can say directly that we observe, in particular in robotics, in automation. Automation, I'm not sure very well, because sometimes we can model a production system using discrete state, but this is more complicated to be explained. Anyway, continuous variable, position, velocity, acceleration. This means once we have a model, once we have the controller, let me say, which is conceived based on continuous system, we can try to discretize this controller. And the example which I proposed last time, let me consider this PI controller, one of the most used. But I told you that the most used is an integral plus state controller. But let me use this one because it's a little bit easier as an introduction of this emulation method. Assuming that this controller is the controller which realizes our goal. Very quickly. This means U of t, the output of the controller, is characterized by this equation here, in which we have Kp as the parameter of the P controller, a Kp divided Ti, our Ki. Do you remember this? Because we have two parameters. Do you remember until now we called Kp and Ki? Here in this notation, I copy from a book. But anyway, the notation, sometimes I am using different notation because we have to be flexible with the notation. In any case, Kp is the parameter of the P controller. You remember, the P controller is in the controller, we react proportional to the error. E, I told you last time, is the difference between what I want to obtain, the reference signal, minus what I have. And now I am trying to proceed a little bit faster than last time. And the Ki is Kp divided Ti. You remember in different courses, probably you learned about the Laplace transform. I don't have here in this short time the possibility to recall the concept of Laplace transform or theorems related to Laplace transform, but I am sure that you learned in the basic control courses the Laplace transform and its applications, I would like to say, but in general also from math. The Laplace transform of this expression here is basically this expression here, in which E capitalized of S is the formal, let me say, symbolic Laplace transform of the function E of t. The Laplace transform function from time into S variable, the complex variable. A little bit, this Laplace transform is quite abstract concept, because try to eliminate, let me say, transform the time, transform in general function of the time into function of the complex variable, to frozen the time somehow. But I don't have time to explain much more. It's not so extremely relevant to recall everything, but I think that the basic knowledge from math is enough. It is enough, because it is enough to remember from math that the Laplace transform of the integral is 1 divided S multiply, of course, the Laplace transform of the function inside the integral. Therefore, I can put in evidence E of S of this expression here when I try to apply the definition of Laplace to this expression here. Of course, Kp Ti, they are constant. If you remember, the definition of Laplace is an integral. This means I can put in evidence because the constant, if Kp Ti are constant, these two parameter constant can be put outside the integral. Now, concept of the discretization. The concept of the discretization is based, first of all, on the concept of the discretization of the time. Discrete system means for us discretization in time. This means I have to discretize, first of all, the variable t, the variable time. And this change really a lot in the dynamic of the system. The dynamics of a discretized system is totally different with the dynamics of the continuous system, totally different. With respect to the stability, with respect to the performances, to the respect of dynamics. Therefore, we have to be careful when we apply these methods, the emulation method, because we have to verify that the characteristics of the specifications are guaranteed. Not always as guaranteed. Let me repeat a little bit what we did last time. I will introduce at the beginning. I don't have much time to tell you about many different methods, but you can see here one of the most important methods, Euler forward. This means we have also an Euler backward. Of course, we have an Euler backward. Look at this. In this controller, the most important part is the integral. Why that? This I told you at the beginning when we introduced the concept of the integral in the controller, because the integral in the controller states and dynamics. States in the memory. The memories represent, do you remember, a state. If you think about the model at the beginning, I told you a little bit some concept about modeling. I told you that in the presence of an integral, we have always a state, because state means for us everything which I can store, everything in which I can save, let me say, roughly speaking. State means not only represent energy, do you remember? But not only the kinetic, potential, electromagnetic, electrostatic. For us, in our general concept, state, or energy, better to say, means everything which I can store, everything which I can dissipate and or store. This means it's not necessarily a physical energy, but could be also a pseudo energy. Money. I can store money, I can dissipate money. Also properties, also assets. I can store asset, I can disseminate, I can discharge, I can destroy property, assets, and so on. In fact, in economics, we consider states, for instance, liability, the money which belongs to me, but the money which is in the bank, assets, and so on. Now, this means very important is to consider what happens for this part here. I mean, to discretize E of t, is enough to say that t, to remember, equals t not capitalized. Last time I told you, but I will come back, k multiply ts, or the k multiply t capitalized, in which k is the counter starting from 0, 1, 2 as natural counter. Counter. Let me go a little bit more in depth here. Exactly what I try to explain now. We will see a little bit later better what I intend, but t multiply equals k multiply t is our discretized time. Our discretized time. Look at this expression here. We have a pseudo state, which is the state of the integral in the controller, which I will call here q of t in continuous, or xi of t as I called until now. And then we can see in its discrete form in which t, the time, is considered k multiply t. It isn't a constant. Could be 1 second. This means t is 0, 1, 2, 3, 4, 5. This is the meaning of this expression here. The meaning of this expression here. I mean, it's not continuous anymore, but in this case, if t is 1 second, I will count each second, starting from 0, and then 1, 2, 3, 4, 5, in accordance to the amplitude of t, discretization time, or sample time. Sometimes t predicts s. That you can see also in my lectures and time I change the notation to. Instead of t, I will write always k multiply t, or ts, t capitalized, as a value, in accordance, let me say, why not, of the resolution of the time. I have a picture to clarify. Let me explain a little bit until here, and then we will come back on this. This means everything which is time, in this expression, I will replace. I will plug in k multiply t capitalized. Easy. Until here, easy. Then, do you remember, we learned at school that an integral can be approximated using the sum of what? Of a counter, which in this case I can call I starting from 0 until k minus 1. I will clarify again now why I am considering this. Of what? Of the variable sampled using my, let me say, criterion. I, because now the index is I, multiply t, everything multiply t. To explain this a little bit better, you remember last time I skipped a couple of slides and I showed you this picture here, which we can see very well. You can find here at the page number 4. I skipped page number 3 basically. Just to should be improved, of course, this lecture, the slide, but anyway. We have the continuous function E of t. Now we can understand a little bit better intuitively the concept of continuous variable and discrete variable. And we can see how I can approximate the surface under the curve. Do you remember in high school? With a stepwise constant continuous function. Stepwise continuous function. We can see here. And of course, we can see from the picture that if I consider smaller and smaller t, we can say that I will approximate better and better the integral. It's intuitive. If instead of k multiply t, I will consider my step to approximate the time, why not? T divided 2 is intuitive that I will have a better approximation of the surface. Question is, with a better approximation of the surface, do we have a better approximation, excuse me, do we have a better dynamics using a better approximation of the surface? I would like to leave this as an open question. It makes sense to ask. Look this, in order to justify a little bit this expression here, and in particular why we are considering k minus 1. Do you remember last time I tried to consider this one, this expression, because if you consider exactly this approximation, the surface characterized by the blue and red surface, the sum of these two surfaces, is characterized, the surface until kt, let me say kt, this means E of k minus 1 multiply t. Let me look here. Probably it's better to look directly here. This surface, which is characterized as the blue surface and, or the plus, the red surface, can be seen as this surface here plus this ak multiply t multiply t. I don't know if it's clear. The surface which we can see here, blue plus red. The past surface plus the actual surface, assuming that kt is the actual point when we are. Makes sense, no? Oh, no, excuse me. Make more sense to think that we are this point here. We are this point here. So we have as I told you, the whole surface which I see. Make more sense. The surface which I see, which is an approximation of the surface under the continuous function E of t at this point here, is the surface which we have here, this blue surface, plus what? This distance multiply t. This means this justifies totally this expression. Because everything is starting, let me say, from 0 until k minus 1. Starting from 0 until here. Because when we are here, in this expression here, we'll consider also this, in accordance of this expression here, which is a e of k minus 1 multiply t. Basically, in our expression, we have both elements, blue and red. At k equals 0, in our case, we have this distance here, multiply t, plus, because in the sum, at k equal 1, we are at this point here, multiply t. Excuse me, at k equal k minus 1, because k is here. The bit to understand, the actual value is here. But to calculate everything, I have to calculate until this point here, the time point before. Therefore, I put here k minus 1. Okay, 2, 3. Now, I already clarified a lot of things. We will leave open this question here. What happens if t is too small? It seems to be an advantage, but we will see if it's too small, it's not an advantage. I will coming back during the lecture today, but in particular next time when I will introduce the model predictive control, because apparently, considering t very small, as I told you last time, we have an advantage. Of course we have. But if too small, we will see that we have some drawbacks. Now, it's interesting because it's not so intuitive, because it seems to be that considering smaller and smaller step time, we can obtain advantages. Of course, in the approximation of the surface, yes. Of course, also in the dynamics, but we cannot be, let me say, infinite small or relative small. I will come back on this. I would like to leave an open problem. Now, what we can say here, that we have the discretization of my controller, in which I discretize E of t in this form here. In which I discretize the integral of its discrete state, or the pseudo state, in which Q here is let me say, is the state of the integral is updated in accordance with this expression. Why that? Because as I told you, the integral is updated, is represent the state, represents the yes, this is a pseudo state, is represent the memory. Now we can see how I can consider here the memory. I consider it that the step after equals the step before of the state plus the update. This is in a surface. This is in a surface. And this is also in a surface. I told you exactly now. I told you using this picture. The surface at this step here, we can call kt plus t, but you can call it as you want. The actual state is the past one, the blue, q of kt, plus a kt multiply t. It's basically, it's written again here if you want. It's written again here. Exactly. In this slide, in this lecture, we have many, let me say, many repetition, if you want. Let me see if I can improve a little bit. Yeah, in some books, you find here k minus 1, everything which multiply t, k minus 1 multiply t, and you can find here k of t, and here again k minus 1, everything multiply t, and then also here k minus 1 multiply t. But it doesn't matter. That's we know. This is most usual notation. Is exactly the surface which I know. And with surface, I can calculate the surface at the step after, let me say, which can be used for the next iteration. It's easy to implement than to explain. Before restarting from the point of last time, probably we stopped here, something like that. I don't remember if I introduced the concept of set. Let me introduce this concept today, eventually. Yeah, I don't remember if I put, probably yes. Which is an extremely important variable, even though at this moment I would like to introduce just using an intuitive concept, the concept of shift. Meaning, I have an x of k. Sometimes we use x of k instead of x of kt, because t is given. It's our interval of time. This t has also a practical meaning, because inside t will run all our operation in the microcontroller. I mean, if you think about this picture here, very important concept in robotics, in automation, and so on. In the microcontroller, to apply U at this time, U is characterized by this expression and this expression. But of course, at time k, is characterized by this expression here. And of course, we will prepare the next step using this expression. Now, everything which I have to calculate, for instance, this, but everything which I have to calculate in this to realize this control, I didn't tell you, I don't have time to tell you about observer, but anything which I need to apply the controller. An observer is something which is useful sometimes to estimate variables which I cannot measure, but I don't have time to tell you about that. Everything which I need to be calculated for the next step must be calculated here inside, or here inside depends where we are. If we are here, I apply u at this point here, k equals 0, but I have this time to calculate, in this case, this expression here, everything which I can be used at this time. I don't know if it can be somehow understood. To do exactly this calculation. I mean, this I measure, assuming that I measure this, but this I have before, but I have to do these calculations inside this sample time. Now, of course, if I were to do just this calculation here, it's not a problem. But sometimes in this T, I have to put many things. For instance, an observer. An observer is a complex algorithm which is really time consuming. This means in a part of this time could be dedicated to the calculation load to realize an observer. What is Z? Coming back to the concept of Z. Z in this context, here we will improve a little bit later when I try to introduce very quickly the zeta transform, which is a similar concept to the S transform, but in discrete format, let me say, in discrete representation. The operator Z is used to denote a forward shift. For instance, Z multiply x of k equal x of k plus 1. More frequently, we use the Z up to minus 1 in order to denote, to indicate, and a shift, yes, but in the past. This is useful to represent our controller as a function of the past value. I thought you wanted now. Q, this Q here, is the function of the past value of Q. We can see here. And with respect to this, the past value of E, because these two elements are calculated at the same time. Let me do an exercise. We go ahead with this exercise. I already told you everything here. I don't need to repeat. Now, look at this example. To apply the shift operator. We have exactly again this expression here. I didn't put here inside the argument t, because t is given, but you can imagine here, practically you have t here when we implement in the program. T is given, therefore I didn't put here. If I apply here the shift operator, as I already told you quickly, but now let me see, or let me show you analytically. I have this expression here is calculated, came from here, no? Is calculated at the same time. This means between this effect here, which came from this cause, we don't have any shifting. Clear, no? KT, KT, KT. Every elements from left to right are calculated at time KT. Therefore, this expression here remains the same. We can see. I didn't change anything from here to here. But this expression here, as I told you before, we have a different, let me say, a different timing, if you want, between left and right. It's not a problem because this expression here can be interpreted that the future value of the integral of the surface, if you want, is the function of the past surface plus the new surface, which can be calculated for a value of the error which I measure, multiply t, which is given. Here t must given. Inside the argument is not necessary to put because it's fixed. It is allowed to say that I will denote the variable, the relative function at time kt. But here must be given because otherwise I don't have a surface. Now, in accordance of our formal definition, we have a z multiply qk, because we have a k plus 1, equals this expression which does not change, because this element here is shifted forward with respect to the all element of the right part. This means in accordance with this formal definition, q of k plus 1 can be seen equals z multiply q of k. Just formally, in accordance with the definition, just considering the definition. Yeah, I didn't change anything because we are at the same time. Here, this expression here came from this expression, just considering q of k on the other part, we have z multiply q of k minus q of k equals e of k multiply t. No? Think about that. This when this appears on the left part, you have minus, and here will disappear. No? Calculation from high school. No? And then I can put in evidence. I can write q of k, which multiplied z minus 1. Again, look, it's an algebraic calculation. Putting this part here, or this element here on the left part, we have q of k, which multiplied z minus 1, because we have a minus q of k, equals e of k multiplied t. Now, from this expression here, I can obtain this, which we can see interesting now, that q of k can be calculated as a function of the error of a function of e of k multiplied t, divide this formal shifting operator. Just in let me say, is in an abstract form, if you like. Plug it in this expression here, plug it in this expression here, I will have this one. Look now, interesting what we have. Doing some algebraic calculation from here to here, what I did, I put just in evidence e of k from this and this. We can see here 1 plus 1 divided ti multiply t divided k minus 1, everything multiply e of k. Again, the problem, how small could be t? We can see a little bit also here the answer. That cannot be extremely small. We can see from here. I don't know if this is visible, because if t is extremely small, it seems to be that I can cancel the effect of the integral. Because the integral is characterized, q of k, the surface, by this expression, which is proportional to t. Do we have an optimal value of t? Of course, we have. But I don't have time to tell you about it. But we have an optimal value of t. But cannot be extremely small. It's written here. Because otherwise, also from here we can see. Because otherwise, the effect of the integral is annihilated because qk, if t is infinitely small, is 0. It's interesting, no? But if you think it makes sense, it makes sense. But of course, we have to think about that we're speaking about a discrete form. This means we have to approximate with a finite surface. No? The integral must be approximated with a finite surface. But I will come back on this. Now, if you compare this expression here, which is a discrete expression, with the continuous expression, which you had at the page number 1, I think, or page number 2, so here, page number 2. Here. You remember at the beginning I told you U of S, the Laplace transform of this expression equal this one. We can see if you compare this expression with this expression, again here U of S is a function of E of S, everything capitalized. Yeah, U of K is a function of E of K. You can put in evidence if you want, is here. No? This means, what is the difference? That S is equal exactly Z minus 1 divided T. Again, S here, excuse me, S here. The difference is, or the formal difference, or if you look at this expression here inside, which characterizes, you remember the concept of the transformation function, no? Transfer function, excuse me. The transfer function is this one. The transfer function, excuse me. The transfer function between, let me say, E of S of U of S in some books, U of F and E of S is this here in S domain. The transfer function in the discrete domain, U of K divided E of K, is exactly this one in which we can say that we have the same expression, or we can say that it's an approximation, because everything came from the approximation of the integral, if S is circa Z minus 1 divided T. Do you remember here we have an S, we didn't have T in the continuous, we have just 1 divided Ti multiply S in the denominator. This means in order to consider that we are considering here as an approximation, of course, S in our context is approximated by Z minus 1 divided T. S is a very side operator. We don't need to learn this nomenclature, no? What is the meaning of this? This is the kernel of our emulation method, or the methods, let me say method, because once we have a controller, in COS, we have seen many controllers in COS at the beginning of our course, or we selected some controllers. Now, this controller can be approximated by the same structure and considering S equals Z minus 1 divided T. This means I realize a discretization just putting this equation, or let's put it this equality, which represent our approximation. Let me look at an example. I think I have also an example in my material. Let me go ahead. Yeah. Look at P of S equal S squared. This is the in the plane, it's in a process, extremely easy, 1 divided S squared. No? Easy to be represented, but with a relatively difficult dynamics, because the system here is unstable. Is internally unstable, externally unstable, is a system quite difficult. Assuming that I am able to control, assuming that I think I have the simulation we will do together. Assuming that this is the controller realize the stability, realize some performances, and we are satisfied with this, assuming that. the name of this controller lead controller, but forget this. For us, it's not important. We are satisfied with this. Loop shape analysis came somewhere, no? Typically using the root logos. I don't know if you learned about root logos, but it doesn't matter. For us, it doesn't matter where this comes from. Can be calculated also with the methods which I presented at the beginning of the course. Now, if I replace S equals Z minus 1 divided T, in order to realize an approximation, please pay attention. In emulation, is always an approximation. If you think how I presented the emulation method, I presented using an approximation of the integral. Let me say in general of the dynamics. I consider just an example, PI. Instead of S here, I plug in S equals Z minus 1 divided T. Believe me, on this calculation, I read this one. Just to simplify. If T equal 1, I have in the simulation, I think, for general T, we will see later. I have also here, I think. For T equal 1, this expression here becomes this. Just to simplify. Of course, the choice of T is not irrelevant in terms of dynamics, because change really the dynamics. You remember a little bit Shannon theorem, aliasing problem. Anyway, I don't have time to analyze this aspect in terms of signal processing, but probably you know a little bit these topics. Of course, we can say we can reduce T, but of course, reducing, do you remember I told you that we can reduce, but we cannot reduce too much. It's also a big problem, this one. But also technically, because inside T, I have to realize all possible calculations. And sometimes the calculation is very heavy if you have an observer, if you have a little different complex control strategy. For T equal 1, this expression becomes this. Now, cheat of Z, let me say the transfer function, U of k divided E of k. It is what? Do you remember the transfer function what? Of the controller, no? Now I lost material, of course. Yeah, one second, please. Just one page, I think, and then we can take a rest a little bit. Then we will come back. With the simulation. Again, I repeat it for you, the transfer function of the controller. This can be written in this form. I multiply by Z. 0,2 can be written 1 divided 5. E of k can be seen here. From here to here, I think. No problem. Why, nevertheless, this calculation? Because the idea is to obtain in a control law, U of k, or in this case, U of k minus 1, or at the end, U of k, does not matter. I will obtain in this form, on this form. I will clarify now. I mean, from here to here is easy, but what is the idea? The idea is to isolate U of k. U of k can be seen from here to here is clear. Z multiply U of k minus 1. I don't know if this is clear. And here, I do the same concept. No? 3 times Z multiply E of k is 3 times E of k plus 1. E of k plus 1, because of this shift forward element. Minus 2 times E of k. Multiply 1 divided 5. 1 divided 5 came from 0,2. This is already our control law. Very often is written in terms of k instead of k plus 1, but this law is exactly this. It depends what I consider for the present, what I consider for the future. But why that? Because what is important It is relation between the left, the effect, and the right, the cause. We can see that this effect equals 3 times E, the error, this effect at time k plus 1, 3 times the error at the same time, like here, minus 2 times of the error at the step before, minus 2 times of the error at the step before, with respect to k minus 1 at the step before. With respect to k plus 1, the step k of a of e of k is this at a at the step before. Excuse me, it's more difficult to explain with words than to read. Again, this expression are the same. Because what's important for us, how I can realize u of k. I show you in simulate. If t is the general t, this means this was the original controller. I didn't put here any t. I didn't put t equal 1. If I do the calculations using general t, here is extremely boring calculations. I do the same calculations, but not for t equal 1. For t equal t, a general t. Believe me, this is really boring. Algebraic calculations. This is the final control law for a general t. Of course, for t equal 1, we collapses in this here. Again, if you remember, just to understand, this was the original control law, let me show the transfer function to be precise, of the controller, which states the control law. For a general t, let me show you again. Okay, yeah. We came from this, you remember? Which I put instead of S for my continuous controller, z minus 1 divided t. I will obtain this. Now, for a general t, I can do the same calculations. And believe me, we will obtain this one. It's easy to see. From here, I obtain this. T is not 1. Of course, for t equal 1, this will cancel. This will be minus 2. Exactly as we have it. Very important for this t equal 1, therefore I consider t equal 1. We cancel, or we see the effect of the previous value of u. This means we have a system with less memory. It's an advantage, it's a drawback. Typically, it's a drawback. I will show you a little bit the simulation, but I will leave this exercise at home. We can do also together. Let me see what I can say. Yeah, this consideration is important. You remember, again, the concept of t very small. The concept of t very small. That it seems to be, in general, that I approximate well the signal, but I don't approximate well in terms of surface, of finite surface. The concept is finite surface, because k is 1, 2, 3, and so on. This means I have to define in the surface. Look, for t equals 0, I have this, but we will cancel here. I have u of k minus 1. This means u of k depends on the past. But here we will cancel, because we have a 3ek minus 3ek. This means that uk equal uk minus 1. We destroy totally the controller, because I am not able to change or to be sensible what happens when signal change, when in general we have an error. Is E, do you remember? I recall E is the difference we call error in the sense the difference what I want to obtain, exactly what I told you at the beginning of the semester, no? The reference signal minus the decided signal. This means if at the end, if t is 0, towards 0, no? We obtain that no differences or small differences between the error at time k and the error at k minus at time k and the error at time k minus 1. This means u of k circa u k minus 1. The control is destroyed. No control actions. Okay, I would like this introduction of discrete system to conclude here. We take a rest a little bit. We will come back, let me say, in 50 minutes, more or less. Let me say 3 o'clock with the Simulink MATLAB. And then we will go ahead with some issues on discrete, but I hope to be able to present at least this integral with the state space controller in order to have an idea about the possible implementation. About the theoretical parts, I will reduce a little bit. Now we will see some issues about backward, about different elements, probably a little bit Z transform, S transform, but I don't have time to go really in depth. We are limiting, we are considering just continuous system, no? At this moment, you have seen S transform, the plane which I'm considering, which I consider now is in 1 divided S square. If the system is not linear, we have to introduce again the Lyapunov, but discrete Lyapunov function or discrete Lyapunov function candidates. The theorem change a little bit nevertheless, but the concepts are always the same. We will see in, I have a message here. We have received, okay. We will see in 20 minutes, more or less. See you later. Let me stop here 1 second. Okay, let me now restart with the simulation of this easy. This example is not so extremely easy, but I think can help to understand. Now, finally, I found the material. Let me look for MATLAB. Okay, I am opening MATLAB, just a second. I am opening MATLAB. Yeah, what we have seen basically is in a controller based on this emulation method. This means assuming that I have a continuous controller which satisfies my specifications. Now we have seen in the first part of the course what is a little bit the meaning of this. And then now, very often in robotics and automation, almost always, we have to implement this controller in discrete form because of different reasons. No? As I told you last time, the reason is very often that, let me share now, that we have at disposition just microcontroller and not other systems based on the operational amplifiers. But why that? Because we have many advantages in discrete controller. Other controllers, we can reprogram very quickly. We can change or test different controller almost simultaneously, and then also the cost, but also some technical advantages. Drawbacks, basically, to guarantee the same performances is not so easy. We will see also now today a little bit intuitively. Two guarantees in the same times, mm, let me say, stability, dynamics. This is not so an easy task. And uh, to guarantee the speediness of the controller. But anyway, I'm not expert about this hardware problems, but anyway, we have drawbacks and advantages. But the big advantage is that we can reprogram, we can easily to realize in a commercial products in this sense. Otherwise, we cannot explain how nowadays the controller, the controller is basically realized in discrete. But very often, in accordance with my experience in industry, a part of the controller is realized in continuous, depends of the speediness, depends of the precision which we want to attain. Because in continuous controller, the advantage is really precise and fast. Okay, independently of this, depends on many things, but just to show say to you that it's not how possible to say everything perfect in discrete. And on the contrary, more perfect in continuous. Therefore, this emulation, we can justify in this sense. Why the idea, one possible idea, impossible method is to realize in continuous, then to approximate. Because sometimes the approximation could be nevertheless could be enough. No? Okay, let me open this. I open this. I hope that can now open. Is exactly the example which I presented today. I need a little bit time to upload. MATLAB is trying opening the file. Let me see if I'm able to read the file. Yeah, let me share now Simulink. Let me comment a little bit. Let me see what I have here. Yeah, it seems this I don't have the case of general T. Let me see if I have somewhere in other. No, I don't have it, but it doesn't matter. I leave you uh, as an exercise for you. Look, we have the continuous structure. I mean, you can see here S square, 1 divided S square, our plane, and here the control. These two blocks represent the control, continuous. I measure the output, I generate the error. Remember, this U of S is E of S multiply these two blocks. Let me show you. So we are Let me switch on the lateral camera to show you exactly this. I didn't have the case of T, but you can realize at home, no? I mean, I have, I didn't find quickly. Let me, but it's easy to implement. No? The controller, 0,2 multiply this transfer function. The controller means U of S divide E of S, if you remember the transfer function concept in the course of control. Of course, must be considered in the loop. No? Yes, must be considered in the loop. I implemented in the loop. And here what I did is the discretization, or better to say, the approximating discretization of this block here, Consider also this, no? We can see here a little bit 1 divided phi, no? 1 divided phi is I multiply by 0,2. I didn't find the general with t. For t, doesn't matter which one. Here is t is equal 1. Try to do at home. It's not difficult. If you want, we can try also together, but I need time. Let me see. Let me see the approximation. I mean, look here. Here we have 3 divided 5 multiply E of k. This block here in MATLAB, the zero order, realize exactly this the sample. Remember, I told you about this this kind of function. Exactly, let me show you what I intend. This is stepwise continuous function. Realize the discretization of what? Of E. At the end, we had it. Where is page number 7? Oh, I don't find it. Here, no? 1 divided 5. We multiply 3 times E of k minus 2 times 1 divided 5, E of k minus 1. Look how I realized this. Hmm? 3 divided 5, which multiply E of k, minus 2 divided 5, which multiply E of k minus 1. Here we have an E of k, thanks to this block which write the sampling. Look here inside what I intended. Let me share. Here inside, we have a t equal 1. Of course, if you realize for each t, you have to put t, but please remember that you have to define t in MATLAB or in an M file. We have seen this exercise also last time. In this case, it's t equal 1. This particular t, which cancel the memory of u. This element here. Okay, let me see the results. Running, let me see. Let me share. This is the result. The yellow is what we obtain with the continuous, good, the bad, forget it, because it's not this is the topic. But we can see that the approximation is not better in the sense. Why that? For instance, it is difficult to judge, but in terms of overlength, the maximal error, we have something which is not really it's less and not so good like yellow. Of course, also the settling time, the time which I will be the error inside 5% of the final value. Of course, we can see eventually that is faster the system, but anyway, it depends what we want to attain. Typically, the error, this means the maximal error, the other parameter, as I told you, the settling time. No, settling time means the time in which I will inside 5%, for instance, or 3% of the final value. This should be as shorter as possible. Is not the case. Question is, there isn't a better T, of course. We can think about an optimization problem of T. It's not the goal of this course, but try to do at home. Try to do at home. If you want, I can do a little bit here. We have a little bit time to implement this law. And of course, at home, try to consider different value of T. Of course, T is a parameter to be optimized. Is a parameter to be optimized. The course is not oriented in optimization, but we do typically this kind of problem in optimization methods to optimize T. Shorter, longer than one, for instance. Let me, as an exercise show you, we can do exactly here. Let me modify this. Modify in the sense, let me realize here another yeah. No, too much. Copy. Let me copy here. Yeah. I copy this. I try to modify. Let me save with another name. Emulation system with T, so we can distinguish with the previous one, with respect to the previous one. In order to compare everything here. Yeah. What I have to do here is not so difficult because I have to realize 1 divided 5, 3 times E of k. This is there. Plus T minus 3, AK minus 1. This means I don't need to do that. I need to change this. Here inside, I will write Let me show you what I changed here. I went inside and let me show you why this. No? 3 divided 5 multiply. Let me write here as in a comment E of k minus A of k, excuse me. And let me write here. Here is in the red color because I didn't define t. No? Here we have a 3 divided 5, which multiply E of k. This is realized sampling. No? But also here inside, I have to go inside. Let me and to put t. No? You remember this concept. And t must be defined. Why that? Because I have a t minus 3 e of k minus 1, 3 multiply e of k. Everything multiplies 0, 2, no? Or divide 5. This we already have. Please pay attention. This t which I put inside this sampling block is here. K multiply t, k multiply t. Realize exactly this. I sample the signal E. Let me show you that I realized already this part. What I have to realize is this 1 minus t multiply E of k minus 1. Let me show you that I realize exactly everything which depends of the E. Do you remember 3 divided 5 multiply E of k and t minus 3 divided 5 multiply, excuse me, here, E of k minus 1, because here is the delay time. Please pay attention. I forgot to say before, this 1 divided set, it's set up to minus 1. This is shifting forward or shift feedback. Typically, we use shifting back. Why that? Because the future cannot be realized in this form here. We will see in model predictive control how I can predict the future, but I cannot realize the future. Therefore, even though we defined the shifting as in shifting forward, but basically we use always shifting back. Here inside, now, let me go here inside. We have to do the same as for the sampling block. We have to declare or to put t instead of 1, because this means we delay the system, the signal in the sense. Somehow we can say the system within t, which can be chosen. Exactly. We realize this expression here. Let me show you 1 minus t now. Multiply u. This memory with respect to u. Here we have the memory with respect to E. Here we have the memory with respect to U. This controller is interesting, already interesting controller. We have 2 memories, one with respect to the error, one with respect to the U. I hope it's not so difficult. I try to simplify everything to explain with really intuition. Now, we have to consider here, as I told you, 1 minus t, uk minus 1. This means I have to consider another plus. Let me consider a rectangular block, probably is better. What is u of k is here? Why u of k? Because everything is in the function of u of k. Did you agree? Now, I can copy this. This means I need this to write 1 minus t. I go inside without sharing, but it's easy to see the results, 1 minus t. I need also the delay because, as I told you, I have to add this element here must be u of k minus 1. Exactly 3 elements. Here we have also 1 minus t multiply u k minus 1. This means now, if I run the simulation putting t equal 1, if no mistakes, this element here should produce the same result as this one. Let me check. Could be that I have some mistakes. How I have to do that? Here again, what we realized, we can see. Let me go in MATLAB. If I put t equal 1, these two results, the output must be the same. Let me come back to Simulink. But good approximation, this is not the topic of today. As an approximation. Okay, now we are waiting here. Does this signal equal this signal? If no mistakes. If mistakes, I leave you as an exercise at home. I have to see just two signals, the yellow signal and another one. Let me see. I hope no mistakes. Another signal typically is red, I don't know what, but the yellow is, yeah, we can see exactly as before, because this red color summarize both. We have just two signals instead of three. Now, t and different value. What do you think? Let me consider smaller t. Let me write. I didn't share, but believe me, I write instead of t equal 1, t equals 0,5. And then I run. Now, we should see three signals. Let me see. Yeah. We can see how it seems to be improved. You remember the blue line, the color is at the beginning is yellow, and then blue. The second color is blue, the second element of the max, and the third is red. Therefore, before we have seen just red because red overlaps. We can see that this is improved. Now, try to do at home to reduce the what happens. But we will see this a little bit better in a more complex controller when we consider, for instance, the model predictive control. Now we reduce a little bit. Let me see. Better. Now, probably I reduced too much. And of course, we need a lot of time to calculate it. Nevertheless, we can see that we have a better approximation. Basically, we, let me say, overlap. We overlap the yellow with the red. But when we have some problems, now it is difficult, no, but we need time. We have some problem, try to do at home. Let me show you. If here in the system, here in the discrete, excuse me, yeah, we have some disturbances. The controller cannot go to react. Try to do at home. Introduce, for instance, it doesn't matter where here, some signals as a disturbance. Some signal as a disturbance. Why cannot react? Because if t is very small, 10 up to minus 6, take up to minus 8, we have this, we will cancel. Because t tended to 0, very small. We have uk equal uk minus 1. This means no reaction. This means if something happens in the loop and a disturbance to be rejected, you remember I told you a little bit about the rejection of disturbance using sliding mode control. Do you remember? This is exactly the same concept. Of course, in the sliding we did continuously, we didn't have this problem. But also, if I discretize, we have the same problem like here. A discrete controller, in case of disturbance, if t is too small, we lose the reaction of the controller because we don't see the differences. Try to do at home. I would like to go ahead because I don't have much time. Could you also a question for the exam? Why not? Considering this file, which you can download, try to simulate a disturbance where, now let me see more concretely. For instance, in the signal here, the goal is 1, no? The goal is 1. But you can here consider, I don't know, let me see. It's a shame I need time, otherwise I can sketch a little bit the idea. Let me see. Just quickly, and then in the exam, eventually I formulate a little bit more precise. Let me consider disturbance under signal routing under sources. Yeah, something like that. Something like uniform random number. Let me put okay, I put it twice. And I have to put also here, no? To compare. Try to do at home a little bit better, no, than me. Now I have too small, otherwise we have to consider really a lot of time. Now let me run. Should be nevertheless visible. One second. Let me see a little bit, for probably too high, the amplitude. Yeah, of course. Let me see, and then I will share just in a second. Simulate something longer. Okay, let me connect and then I will comment the results. What I did, okay. Okay, I will show you probably here. Second, yeah, can be better see. Yeah, it's visible. Let me share. Look at this. This is the controller with t equal 1, which is not the best one. No, it's nevertheless not extremely small. It's not the optimal one because should be possible to define an optimal problem inside this control problem. It's not the goal of this course. I hold here a lecture on optimization, no? In which I consider exactly such kind of problems. But look, nevertheless, even though you can, I can simulate longer too. No, we can see that nevertheless we achieve one somewhere. No, it's not so nice, but we can achieve this. Look what happens. Let me come back here. If I look now here where t is not 1, I put t up to -3. I will show you. Look. T 10 up to -3. This is the way to represent 10 up to -3. Look what happens. If you check here, now we can see the differences. This is the output, which t is 10 up to -3 as an error. It's not around 1. Why that? Because the controller does not react to disturbances. Just a little bit intuitive. You know? Of course, this lecture can be improved, but in accordance with the time which I have, yeah, this is a little bit what I intend to. Do you remember? In the continuous, we have seen that the integral realized in a robust controller. If we are considering a constant as a, let me say, or relative robust, depends on reference and a constant reference, a reference which is constant. Now, also in sliding, if we discretize the sliding, if you do a discretization of sliding, t should be not extremely small for these reasons, because otherwise the controller does not react. We have seen in this example. I don't have time to introduce the discrete sliding mode control, but at the end I flesh out a little bit the idea. But this TTS, the simple time, we have seen also in these examples, cannot be arbitrarily small. There is no optimal, no? But of course, this belongs to another course, optimal control. Okay, give me a couple minutes to choose the material. Let me stop a little bit. Okay, now I would like to put some issues, some questions. Stability, method. We have seen forward Euler. Let me see another methods in order to have a feeling, at least a feeling that we can have different method of discretizations. These methods are also valid in general for nonlinear systems. This means not necessarily valid for linear systems, can be applied for any kind of systems. But of course, the topic now, which I will consider in terms of stability exactly now, is related to the linear system. Nevertheless, I will flesh out a little bit what changed. in term if the system is nonlinear. Okay, let me go ahead with the lateral camera. Relatively quickly because it's just to inform you a little bit. It's not. I don't want to consider different discrete. It could be eventually backward. Could appear in the exam. But of course, method as Runge-Kutta or in trapezoidal methods, we will see that you have to know that there exist many ways to approximate and continuous system, but for the exam, forward Euler or implicit Euler, eventually backward Euler, yeah, this can be considered, but the rest you have just to know that they exist because we don't have time to go in depth. Look, explicit Euler is what we have seen in the context until now. No, we called a forward Euler. This is in a forward Euler. You can see that can be applied also for nonlinear system. F is basically the notation for nonlinear system. And at the end, we obtain always a function x of k, the actual value, as a function of x of k minus 1 and u of k minus 1. This is always possible in case on forward Euler. Therefore, the name explicit, because we can see that we have an explicit expression of xk as a function of xk minus 1. Basically, the actual states depends on the states at step before. Could be also such kind of discretization. In this sense, we speak about implicit, because we can see that xk is present here, is also present also here. And this is the typical example in case of Becquerel Euler, but for nonlinear system. That's in general, let me say. F is in general. In linear system, nevertheless, also with Becquerel, we are able to obtain something like that. Here, nevertheless, could be uk minus 1 and uk, but very important, the states. Basically, explicit is related to the states. Yes, implicit, because xk is a function of xk. Something like we cannot apply, no? We cannot apply because today is a function of today. Or if you want tomorrow, it's a function of tomorrow. U can be also u, okay, in both cases. The reason is that we have a u. Because it's the output of the control. Also, in case of the controller, it's the same concept. What we have seen until now, a uk, we have seen for t equal 1 was in a function of uk or uk minus 1, or in case of t not 1, we had u of k minus 1. Do you remember this? This is exactly the f represents somehow the controller. Just a little bit quickly. What happens in Becquerel Euler? It could happen something like that. But of course, if the system is linear, we can realize nevertheless an explicit form. But of course, if the controller is not linear, we have some problems. About backward and forward Euler, yeah, I don't have time to tell you in depth, but we can see here some sentences. Basically, how possible to say backward Euler presents some advantages when is applicable, or if we are able to apply this. The reason is, in any case, we nevertheless have an explicit form. Otherwise, we cannot apply. I mean, this kind of controller cannot be applied because UK depends on UK. But with some approximations, let me say in general, with some tricks, we can, in general, in linear system, we can nevertheless apply, always. And the backward at let me say, some advantage because we have some better dynamics in terms of less oscillation, even in the presence of large sample times. Now we will see now a little bit what I intend. In forward Euler for large sample time, we can also end up in instability. No? We will see now a little bit better, probably with some example. But of course, the drawback for backward is that we have to very often approximate the control law, if we are speaking about the control law, in order to obtain an explicit form. Because in general, of course, if the controller is linear, no problems. We can always realize an explicit form. But otherwise, we have to use some tricks, sometimes to simplify, to approximate, and this could generate errors. Let me see if I forgot to say something. I can tell you something more about forward and backward, but I told you very few words about the relative degrees. Do you remember between input and output? Do you remember this? Forward Euler had the advantage that, for instance, maintains the relative degree between input and output. This could be sometimes an advantage because we don't change. Basically, in some applications, we will see model predictive control, the nature of the model. But could be also positive if we change the relative degrees in, let me say, in some application or prediction. Anyway, this I don't want to say it is necessarily a drawback from backward, but we have to be careful because we change the nature of the model in a sense with backward. But this is a little bit more complicated. It's dedicated, this chapter here, or these considerations, to course more in depth on discrete or discretization. Forward maintains the relative degrees. And some model-based control strategies could be an advantage. We will see we will see a model-based starting from next week. The strategy is model predictive control. At this moment, we didn't see any model-based control strategy. Okay, this is just to inform you. Let me go ahead a little bit more formal. Just introduces the concepts of the stability. At least the concept of the stability I would like to introduce because it's the most important. You have a system. Let me consider a linear system. F is a parameter, G is a parameter, C is a parameter. A coefficient, just a system with just one state, just to give you an intuition. But we can do similar consideration if we have a matrix A, remember matrix B, matrix C, but let me intuitively, because otherwise I need too much time. Impulse response in the context of discrete form means yi of k, initial condition 0, but I put an input at time 0 equal 1. Now, this is the concept of impulse response in discrete. But of course, for any k not 0, u of k is 0. I don't know if it's clear what is this. It's extremely easy. When I start, I put 1 and then 0. State, initial state is 0. At k equals 0, no? At k equal 1 and 2 and 3 is on at 0. Look, This means if you consider now what we have here, we have that for k larger, let me say, if you put here, for instance, 0, you put here 1, we have that x1 is equal g. Did you agree? x1 is equal g. And yeah, let me see exactly what we have here. And x1 is equal f multiplied 0 plus g multiplied 1. Exactly what I told you until now. This means for k equals 0, we have y at k equals 0, c multiply 0, basically, as I told you before. We will see this relation later, no? But read here, no? Clear, as I told you with words. We have seen that x1 and g equal g multiply 1. This means what happens at x a time or the k equal to x2 is f multiply g multiply 1 because this is x1. K equal 1. This means x at 2 equals f x1, which is g multiply 1, plus g multiply 0, because u1 is 0. You can see here. U at 1, better to say this. And then you can do the same calculations for step k equal 2, and so on. We can see now, excuse me, k equal 1, that the output is c multiply g this time. Why that? Because x at k1 is g multiply 1. And if you do ahead the calculations, believe me, we will obtain this, which I anticipated here. I mean, the idea is to demonstrate this, using this easy consideration, the iterations, which in general is c multiply xk. But explicitly, we as a function of the element of the system, C, F, and G, it is one. Believe me, if you iterate until a general K, we will obtain this, which in general is C multiply xk, but xk is F up to k minus 1 multiply G. If you look here, we can see 3, 2. Now I didn't put 4, 3, but believe me, it is easy to do. Meaning of this. Look at this expression here. And if you think about the concept of the stability, or better to say, asymptotical stability, or we can say that in a system of the first order means one state is asymptotically stable if and only if f, the coefficient f, is less than 1. This means that the limit for k to infinite of y of k is equal to 0. I don't know if you remember in math. If this is less than 1, which is to 0. Of course, if the system consists of more than one state, yeah, the situation is a bit more complex because this easy consideration cannot be done. And then we can demonstrate that we have to look at the eigenvalues of the matrix A. In particular, we have to look at the magnitude of the eigenvalues of the matrix A, and this must be less. Let me go ahead. Let me say quickly, less than 1. The eigenvalue can be also imaginary eigenvalue. Let me a little bit go ahead faster, because I don't have time to go in depth on this mathematical aspect, but we can demonstrate that the amplitude means the magnitude of the eigenvalue, which could be also imaginary, could be complex, must be here inside. Nevertheless, in order to understand a little bit better, let me transform these equations here, even though the first order, with the shift operator z. Look, this expression here is equal to this one, because z multiply x of k equal x of k plus 1, in accordance with our formal definition. In this sense, if I put this on the other side, I have this expression here and just put in evidence x of k. Easy, as before, as we did before. This means x of k, easy calculation, can be calculated, can be seen in this form. Now, using, do you remember, u epsilon k equals c multiply x of k, I can write this expression in this form. This is enough to multiply by c. Easy. Now we can see a little bit this idea here. Of course, here is a little bit sketched, because of course, f it was in a scalar, but if you consider in a general scalar, also complex, can be guessed this here. But of course, to be more precise, I have to consider the eigenvalue of impossible matrix, because in general, you remember systems, this idea, linear systems must be not, but could be, let me say, represented in form of matrices. Okay, a few things. Let me see what I have to tell you now quickly. I think I can tell you about this. Yeah, I would like to tell you about this. Let me see. One second. As I told you, it could be that should be better. I don't know if it's the case to. One second, because it could be that better to. It could be better this one, I think. Let me go ahead with this. Yeah, this is better to proceed slowly. Graphical interpretation, slowly, but starting from this. So graphical interpretation of forward Euler, in order to understand, I told you about the region of stability. Do you remember? Quickly. Do you remember I told you that S was equal, or that circa equals, let me see, equal in this sense, in order to understand the relation. S equals z minus 1 divided t. Do you remember? S equals z minus 1 divided t, or z equals ts plus 1. This means, do you remember the region of stability in S, which is the left semiplane? is mapped, thanks to this transformation, in a semi-plane, which is left, but with respect to the line real z equal 1. We can see from here. No? Mathematically can be seen a little bit better, but look, for s equals 0, we have a z equal 1. We can demonstrate that of this, let me say, axis here is mapped on this axis here. And all elements of this is basically on the left of this, or all element of the semi-axis here is from 1 toward infinite, minus infinite, in real part. This means not for all elements of the stable semiplane we have a stable element in Z, because we don't have a map one-to-one inside this cycle. And this depends of T. I don't have time to do example too, but it's understandable. No? A little bit is understandable, this concept here. It could be that in a point here, somehow, for some T, it's not necessarily inside here. Just keep in mind the concept. Let me see here. We have the graphical interpretation of backward, but should be better if I introduce backward, which is not here. Let me see if I find. One second. Where is? I am mixing the slide now. This is the problem. Because I didn't told you about backward. I told you at the beginning. Let me see. Let me see. 1 second. There are a lot of now material here. Where I told you about backward. I'm looking for backward, but I don't find. One second, let me see if I find. I don't want to waste. It's not waste, but should be nice if I find, because otherwise I have to dedicate time to. Oh, where is? 1 second, I don't find anymore the material. Since I told you. Where is? 1 second again. I think I told you. Where is here? Just a second. Let me stop so I find the material. It should be better. Excuse me again for the confusion which I did in the slides because here in the lab it's difficult to organize the material, to have the material at disposition. We have seen now this, excuse me here, the correspondence, this graphical interpretation in terms of the correspondence between S and Z, S and Z. And we have seen that depending on T, we can have a stability or not. Very important. Please remember, it's not so explained in depth, but we can understand. This stable region, linear system, is not necessarily stable in discrete. Do you remember we didn't demonstrate, but intuitively we have seen that we have to remain here inside. This transformation does not guarantee. This is a drawback, of course. This is a drawback. Before interpreting backward, let me do some calculation with backward or introduce backward. What is backward? Basically, the difference between Euler, Euler forward, the forward Euler, which is here. Do you remember? Until now, we work with this. Q of k plus 1 equal Q of k plus E of k multiply t. This is the blue, red surface. No? It's the blue surface. In our original representation is the red surface. Here, the representation is a little bit different in the sense that we'll consider the A of k plus 1 as the element to calculate the approximation. What is the meaning of this? Let me reconsider if I find the original slides. Some material here is is it? Hope I have another better one. Yeah, here. Backward was that starting from here, we can see here, I will calculate this surface, which is under the curve, multiply E of k, multiply t. This rectangular blue surface. In the backward, we approximate back. Yeah, in blue, we approximate forward. Why that? Because the approximation of the integral is approximated from the over part. Because each time we will consider this multiply this. We consider this multiply again t. But in particular, the surface, the red surface, which approximate the surface which we can see in the picture, is Q of k, the red, plus E of k plus 1, exactly as I told you. Basically, the red plus E of k plus 1 multiply t. T is always the same here and here. Assuming that I know this one. It's a little bit abstract, because typically I don't have this. Now, if the system is linear, please pay attention. I can nevertheless explicit to have a model. But if it's not linear, not necessarily is possible. Therefore, we have an implicit form. That's a little bit difficult to understand, but let me see if doing the calculations, I can express this. Look here. Here we have now, let me see. Yeah. I'm considering backward with the shifting operator. There is this expression in Z multiply Q of k, which can be written in this form, We can see that in our system, the system is linear. It is possible to have an explicit form. What is the meaning of explicit form? The explicit form is Q of k as a function of E of k. because I can write E of k plus 1, Z multiply E of k, and then I can obtain this. I can obtain this explicit, but because it's linear. If it's not linear, of course, I cannot explicit. The reason is I am assuming that I know this value. But typically, I don't know this future value. I can predict it in a linear system. If not linear, not always. Again, this was an integral. You remember, this was an integral. This means now S is approximated in this form, Z minus 1 divided ZT, because this is 1 divided S. Do you remember? This expression is 1 divided S. This means now we have this approximation of S in case of backward, yeah. This means, of course, try to do at home if you want to approximate the controller using backward. It's an exercise. I don't have time to do, but we understood how we can do. We have a different representation. Try to do, please pay attention, what we did until now in Simulink with large T, we will obtain instability. Here, we will always have stability. I don't have time to simulate this. Now, nevertheless, I simulate what I did before for forward. Forward, if you have large T, we have instability. Backward, in linear system, of course, we have stability for each T. How I can demonstrate? I will demonstrate in a few minutes. Let me show you forward with large T in the case which we have seen before. Let me switch here. This is another advantage using backward. But of course, the system must be linear to obtain necessarily, to have the, to be sure that we can apply or we can find the expression, the control law, without approximating. Let me switch. Yeah, let me consider, I don't know, T equals 3. One second, because let's see. T equals 3, for instance. Let me switch. Here. Let me show you what happens here. Let me show. Look, what I told you, not for all T, the forward Euler guarantees the stability. We can see here. Let me show you that I am unstable. But why I am unstable? Let me come back. What I told you until now. I told you that the eigenvalue, where is this? Yeah, here. In general, the eigenvalues, or this coefficient here, could be also complex, must be here inside. Roughly speaking, between 1 and minus 1 if f is real. In our case, in our controller, what is the eigenvalues? Let me show you. Or what we have to check. Let's forget at this moment the eigenvalue because I didn't insist much on this concept. I think not in discrete, but in continuous we know. Look here, the variable which must be considered is this. When this here, or better to say, when 1 minus t is larger than 1 or less than minus 1, we have problems. Why that? That is easy to see intuitively. Why this concept? Because we have that the present, let me say, is larger than the past. If this is larger than 1. Let me show. Yeah, we can see from here. No? In this sense, this we have a problem if this coefficient is larger than 1.
Aber Paul,
Ja, aber das ist fast fertig. Gut.
mach mir aus.
Ja, ist ja auch da.
Nee, Jan ist nicht da. Spät. Ich komme noch keine auf.
Wie ist gegangen? Genau.
Aber ich erzähle später.
Donnerstag ja auch gerade das Projekt, wenn ich wusste, ich hätte dich kontaktiert. Aber denke, Janis hat Antworten von zu Hause. Ne? Aber wir brauchen eine kurze Übersetzung mit Facebook.
Ja, dann schick mir, was du brauchst.
Ich gucke mal, ob Janis beantwortet hat.
Ja, kannst du das auch
Weil bis jetzt hat er uns geholfen. Excuse me, just a second. Es gab ein paar Arbeitsblätter, die wohl in den DFG-Portalen in German. Alle Anträge sind Englisch, total. Aber sie wurde Title, wir haben noch eine Apostille, aber kein Problem. Wenn Sie an mich geschenkt sind, ich schicke dir.
Ja.
Weil ich habe ihn gesendet, wann war am Wochenende, was war, wir brauchen etwas, er war hier, als er mir geholfen, dass er weiß, worum ging nur das.
Ja, aber schick mir das, was du gesetzt haben willst, und mach das.
Ja, hier ist wie eine Offenheit, die ist furchtbar. Weil dir ist auch schlimmer, ne?
Ich bin unten im Keller, drüben.
Ja, das ist
das
gut.
Da ist kalt.
Aber ich kann nicht so runter.
Ja. Hast du Fenster nicht?
Ja, habe ich. Also ich habe gemerkt, dass es ist.
Ja, sehr warm.
Ich habe angefangen hier um halb 1.
Okay, Paul, wir sehen uns später.
Kein Problem. Ich bin hier, ich sage so bis später, habe viel zu tun. Ist ein Problem. Ich hoffe, dass diese von ist in Israel, wo ist diese in Japan, wenn wir machen, es ist einfach aber wirklich, das ist ein neuer Arbeit. Das Problem auch, diese Leute dort sind beschäftigt, gibt es Deadline jetzt im Juni, ne, ich verstehe auch, die sagen ja, Stefan, dieser Friedrich, kennst du es?
Ja,
Die ist einer der Chefs, die macht das, deswegen die. Genau. Jede Zeit, ich kann sagen, dass ich wieder dafür danach.
Wann bist du ungefähr durch?
Sagen wir so 20 Minuten, jetzt muss ich nachholen, ein paar Minuten. Weil
Na, dann machen wir in Ruhe und trinken in Ruhe einen Kaffee. Ich komme dann so um halb sechs noch.
genau. Später. Yeah, excuse me again, but it's clear, no, that in any case, this could be basically this is somehow a problem, no? The sense. Let me show you if t, for instance, is now t was 3, no? Right? Let me see. Yeah, let me see. T equals 2,1. Did you see? No? Now, let me see in Simulink. Again. Because 1 minus 2,1 is outside. Is minus 1,1. Minus 1,1. Now, what we see, of course, is not from the control point of view, not extremely good, but anyway, the goal was one, stable, at least. Again, with this, the optimal T must be calculated. But what I did, let me excuse me, I put it in a value such that we are inside -1 and 1, no? Assuming that is real in this case, because 1 minus 1,9 means minus 0,9. And this means we are inside -1 and 1. Yeah, we have oscillations. I don't have time to clarify why we have oscillations, but the reason is with negative values here, a practical reason mathematically can be improved, this demonstration, but I don't have time. One value is positive, one value is negative. If you consider that I can replace values at each time, no, once is positive, once is negative, depends of k. Let me go ahead to conclude with this discretization. And next week, I will do the controller and practical controller, which can be used in the exam. And then we will directly start with model predicted control. To conclude this let me say, intuitive interpretation of the discretization, let me introduce another, let me switch, another one, OIN method, also called trapezoidal method. This means, look this intuitively. We approximate the surface with a trapezoid. Is here. Q of k, the preview, which is approximated previously as in a trapezoidal system, which is this one. I don't know if you remember in high school. This surface here, the last surface is this plus this, multiply this, divided 2, you know from high school. During doing the calculations, let me say, now the problem is to find, yeah, believe me that they are just calculations. No? This is exactly what I told you until now. I can consider the shifting. Instead of this expression, I can put zeta q of k here, the same. And if I do this boring calculation, believe me, we obtain, at the end, this is in a q, this is in a q. We obtain at the end q of k, something like that, multiply e of k. Sometimes, very often, we consider u of k q of z, and e of k e of z capitalized because probably you learned about the zeta transformation, because we have an expression thanks to the shift operator just in terms of z. Also before we can consider q of z and e of z also before, because nevertheless we have a transfer function, a function of z also before, but I introduced just now. We can see that's the same. We can consider so, we can consider so. Again, comparing the concept of the integral in continuous, q of s, 1 divided s, e of s, we can, believe me, we can see that in case of OIN approximation, we have something like that. S is approximated this expression. Let me see if I forgot to say something, and then we can sum up everything, forward, backward, backward, OIN rules. Okay, I think we can conclude with the last slides. Next week, we will see a controller. It's not difficult to introduce and to solve the problem. The controller, let me see next time, because so we have nevertheless everything which we need, in particular this expression here, which I would like to introduce today. Next week, we will start with the chapter of the exam exercise, considering an integral controller. I would like to use directly, let me say directly MATLAB. No? But let me conclude these 10 minutes with this. Again, you remember this easy concept of set transform, of the variable set shifting. In this case, shifting back. It's very easy to introduce the set operator. The set operator is extremely complex. Look here. Xk has been obtained by sampling and continuous time signal x of t. The formal operator set up to -1 can be defined as follows. Please pay attention. Set up to -1 x of k. I don't know if you remember in control that x of k minus 1 can be seen in this form. I don't know if you remember this delayed system. I don't know if you remember this. Can be demonstrated that exponential function up to minus st, exponential function up to minus st, which multiply x of t calculated at t equals k multiply t. I don't know if you, it is a little bit, how possible to say, it could be, yeah, we can see, for instance, in this form. I have to recall some property from control, but probably you remember this. If you remember this, now it's clear that z, because of this equality, is equal exponential function up to st. And this is extremely important expression because state the exact transformation between S and Z, but exact in the sense that, look, if logarithmical structure, this means also exact, but mathematical exact, because logarithm and exponential as in function, they are function that practically must be approximated somehow. I don't know if I have a material to clarify this. Let me see if I have something here. I don't have here, it's a shame, but this expression here, or better to say, look here. But also here, this product here states the delay of this signal of the, with the time t, t capitalized clock. Basically, at the end here, at the end, we have this product generate x of t not capitalized minus t capitalized, calculated, in our case, at t equal kt, because we are working in discrete. Therefore, the equality holds for discrete. This means we have this. Because T is equal K multiplied T. This we have to do, if you look in some books, I don't have here, it's a shame. The continuous delayed system. This is equals x of t minus t capitalized. If I calculate that t not capitalized k equals kt, because we are in the context of discrete, I will obtain this here, basically. Or if you want this, which is equal to this one. We have a better explanation, but believe me, can be interpreted if you remember this delayed continuous system. Of course, it's precise, it's exact, not precise, it's exact. But of course, what is the meaning of the exact? Nevertheless, practically we have to approximate. We will see a little bit next week with the calculation with MATLAB. MATLAB offer the possibility to obtain this. We can see if I approximate logarithm, Owen's method is the approximation at the first order, you can see here, of this expression. S equal to, remember, 2 divided t, z minus 1 divided z plus 1. What happens if the system is not linear, if the control is not linear, if everything which we have, it is enough one thing that we have in the control structure is controller or, yeah, and eventually system not, we have to work again with diagonals. This means we have to look if exist a positive defined function v of k h, something like less exist, let me say k star, such that the happen of candidate, just roughly, which we have in a positive, again, positive decreasing over time, because k represents the time, exists x star. It's similar as before, it's clear. Here is a little bit different, but not much different, because remember, the derivative must be 0, still less than 0. Here it's similar. For a positive candidate, Lyapunov function. Just never an idea. Is I don't have time, of course, to tell you about the nonlinear Lyapunov structure, but the concept is the same. Again, to fix the idea is not the goal of this course. What is this? It's something related to the derivative. V of k minus V of k plus 1 divided t simple time less than 0. No, excuse me, the contrary. Decrease, excuse me. This means but this means also just roughly, Let me see if I made mistakes again. No, it's okay. This means decreasing, this V over time. Excuse me, now it's correct. It's related, nevertheless, to something like. This V is decreasing. Because the actual is grosser than the future, or the past is grosser than the actual. This means the degrees exist in the value which we have this. By the way, I don't have time just to flesh out that's what we learned concerning Lyapunov. We did some exercise in continuous, can be extended. Of course, it's not immediate, but this is a little bit the idea. I don't have time to tell you about that. Very often, we work directly in continuous, and then we leave the approximation to the computer in practical application, in robotics and automation. Very often, this discrete Lyapunov structures, something more theoretical, even though sometimes important. It's important, but typically, in accordance with what I told you also today, last time, with this emulation. This emulation we can find an optimal T or the TS in the sample time, which nevertheless we guarantees somehow the stability, not only the performances. This means this optimal T. Yeah, next week we will start with this exam exercise, which I have in mind directly with MATLAB, because also in the exam I don't ask about these methods, but to have in mind, I will upload the material to have in mind that these methods, where they come from, implication and so on, would be useful. No question about the non-linear discrete structure, but just fleshing out. The reason is also we have seen this introduced this emulation. This means we do everything in continuous, then we discretize, but we have to have in mind the concept in order to understand when works, when not works. Do you remember exactly the last example, no? T larger than 2, unstable, and we know why. Even though everything was calculated in continuous, this knowledge must be kept in mind. Of course, in non-linear, I don't have time. Nevertheless, this concept of Lyapunov, or even though flesh out, can help. But it's not the course, not the topic of the course. Okay, next week we start with this example with MATLAB to analyze, and I think I have an integral and state space, which we know in continuous. And we use also this, again, this implementation through emulation, because very often is used in practical automation, particularly about soil robotics. And then we will start directly with the sliding mode control. And then we will see this. In any case, sliding mode control must be done, but we have 2 lectures. I don't know if I have time to introduce a little bit the concept of the observer, but this is less important than the MPC, because again, the course is control. Of course, in the control can be also insert an observer, because very often it's useful in the observer to estimate variables which we cannot measure, or to estimate variables which is too expansive to be measured. The observer is itself and control the system, but I don't know if I have time. But in any case, MPC I have time. If I have a question here, I will reorganize this material which I have here, totally confused in my lab. I scan, I will upload with this Simulink, and next week we will go ahead with the program. We have 2 lectures in accordance with the calendar which I saw in your university, but I'm not sure. If I have 3, I am more happy, so I can tell you about the observer, but I'm not sure if I have 3 lectures. We will discuss next time. Thank you for your attention. Nice.
Thank you. Goodbye.
Thank you for the participation.
See you next week.
Nice.